All right, welcome. Today we're going to roll up our sleeves and tackle a classic problem from I.E. Irodov's physics problem book, a book that's famous, or maybe infamous, for stumping students for decades. But don't worry, we're going to break it down piece by piece, and you'll see that even these tough problems are totally manageable when you have the right game plan.
So here it is, in all its glory, problem 1.125. It's basically asking us for two different things about the power of gravity on a projectile. First, the instantaneous power, which means at any given moment, and second, the mean power, which is the average over the entire trip. Now, I get it. Seeing a problem phrased like this can look a bit scary, but trust me, we're going to peel back the layers and find some really simple, elegant physics inside.
Okay, let's get into it. Now, before we even try to solve anything, we need to gather our tools. Any good mechanic will tell you you need to lay out your tools before you start working on the engine. So let's review the key physics concepts that are going to make this whole thing click into place. So let's call this our physics toolkit. We're just going to quickly go over the fundamental definitions we'll need. Honestly, getting these crystal clear in your head right now is the secret. It's going to prevent a ton of confusion down the road. Tool number 1, instantaneous power. Think of it as a snapshot. What's a power doing at this exact moment in time? The way we calculate it is with a dot product between the force vector and the velocity vector. And remember, the dot product spits out a single number, a scalar, not another vector. It's basically answering the question, how much is the force helping or hurting the motion right now? Next up, mean power. This is completely different. Here, we're zooming out. We don't care about the moment-to-moment snapshots anymore. We're looking at the big picture. You figure out the total work done by the force over the entire journey from start to finish, and then you just divide it by how long the whole trip took. It's a simple average. And finally, let's just quickly nail down the specifics of our projectile's motion. We're making a big assumption here, and it's that we can ignore air resistance. That makes our lives way easier, because it means the only force acting on the body is gravity. And gravity is constant, always pulling straight down. We'll call that the negative J direction. The velocity, on the other hand, is changing. Its vertical part is constantly being tweaked by that relentless downward pull of gravity. All right, toolkit's all laid out. We've got our concepts ready. Let's put them to work and solve the first part of this puzzle. Finding that instantaneous power as a function of time.
We're going to start right with the definition we just pulled from our toolkit. Instantaneous power, P of t, is just the dot product of the force of gravity vector and the velocity vector at any time t. So let's break these vectors down into their horizontal and vertical components, their i's and j's. The force of gravity is super simple. It doesn't pull left or right at all, so its horizontal or I component is just 0. It only pulls down, so its vertical or j component is negative mj. The velocity is a bit more involved, right? The horizontal part, v0 cos alpha, never changes, but the vertical part, v0 sine alpha, has to fight against gravity, so we subtract that gt term. Now for the magic of the dot product. You just multiply the matching components together and add them up. And this is where things get really nice. Look at the horizontal I components. We have a 0 from the force vector. So 0 times anything is 0. That whole first term just vanishes. This tells us something huge. The horizontal motion contributes absolutely nothing to the power developed by gravity. So after we clean that up and distribute the negative sign, this is what we're left with. The instantaneous power at any time t is mg times the quantity gt minus v0 sine alpha. And that's it. That is the complete answer for the first part of the problem.
But an equation is pretty useless if we don't understand what it's telling us. So let's actually interpret this. Right at the beginning, when t is small, the power is negative. Why? Well, gravity is pulling down, but the object is moving up. They're working against each other, so gravity is taking energy out of the object. Now, what about at the very peak of the flight? For just a split second, the vertical velocity is 0. And if you plug that into the equation, you see the power is 0. Makes perfect sense. Then, on the way down, the power becomes positive, because now gravity and the direction of motion are on the same team. Gravity is doing positive work, putting energy back into the object.
Okay, on to part 2, the mean power puzzle. Now this is where you can really show your physics chops. You could grab the equation we just found and do a whole bunch of calculus to find the average, but there's a much smarter and more elegant way to solve this.
So before we even touch the mean power formula, let's just take a step back and ask a more fundamental question. Remember, mean power is just total work divided by total time. So let's forget about power for a second and just ask, what is the total work that gravity does over the entire flight? This is a classic crossroads you'll find in so many physics problems. You've got the hard way, the brute force, calculus-heavy path. It'll work, but it's messy and there are lots of places to make a mistake. And then you have the smart way, the elegant way, the way that uses a core physics concept to make the problem almost trivial. And here is that core concept. Gravity is what we call a conservative force. Now that's a fancy-sounding term, but all it really means is that gravity doesn't care about the loopy, scenic route the projectile took through the air. It only cares about two things, where you started vertically and where you ended vertically. That's it. The work it does is all about the change in height, delta y. Now let's read the problem statement again very carefully. It asks for the mean power over the whole time of motion. We can safely assume this means the projectile was launched from some height and it lands at that exact same height. It completes its full trajectory.
So what is its total vertical displacement? What's its net change in height after the whole journey is over? Well, it went up, and then it came all the way back down to the exact same level it started from. So its net change in height is zero. Zilch. Nothing. This is the key that unlocks everything.
And if the work done by gravity only cares about that change in height, and the total change in height is zero, well, you know what that means. The total work done by gravity over the entire flight has to be zero. Sure, it did negative work on the way up, but it did the exact same amount of positive work on the way down. They perfectly canceled each other out. So now we go back to our formula for mean power. It's the total work divided by the total time. And if your total work on top is a big fat zero, it doesn't matter how long the flight took. Zero divided by anything is just zero. And we're done. No calculus, no complicated algebra, just one beautiful, simple, physical insight.
So, we did it. We solved a tricky Irodov problem. Let's just take a moment to recap what we've really learned here, beyond just the answers. What are the big ideas you should walk away with? The absolute most important lesson here is understanding the crucial difference between instantaneous and mean power. They are not the same thing. Instantaneous power is dynamic. It's alive. It's changing every single moment. But mean power is the 30,000-foot view, the average over the whole trip. And for a conservative force like gravity, over a round trip back to the starting height, that average is always zero. And finally, here are some common pitfalls you should try to avoid. First, be so careful with your vectors and scalars. Know when you're using a dot product and what it gives you. Second, whenever you see the word mean or average, that's a huge signal to think about the entire interval, not just a single point. And most importantly, always be on the lookout for a conceptual shortcut. Don't just be a human calculator, be a physicist. Think about the principles first. So, I'll leave you with a final thought to chew on. Our whole solution depended on gravity being a conservative force. But what if we had to account for something like air resistance? Air resistance is a non-conservative force. It always opposes motion. How would that change the total work done? And what would that do to our answer for the mean power? It's a fantastic question to think about. Thanks so much for joining me.